solar cooling systems are a viable solution to reducing the carbon footprint of air conditioning in buildings. The use of absorption chiller systems powered by solar thermal collectors are increasing, but few studies focus on how to improve the solar fraction of these systems with various thermal energy storage (TES) options. More specifically, no study has compared water and phase change materials as the storage medium for TES on the same system. There has also been limited study on cold thermal storage, particularly in using it to increase overall solar fraction rather than load shift. There has also been little focus on control strategies to reduce energy consumption and increase solar fraction. In this study, 6 models were created in TRNSYS and 97 simulations were conducted with different scenarios, all based in Brisbane, Queensland, Australia. Variables were the size and configuration of the solar collectors and the type and volume of thermal storage. Through this process, 2 new designs were developed. A system designed for PCM thermal storage to maximize material phase change, and B. a system designed for cold thermal storage for chilled water from an absorption chiller that is able to simultaneously store excess cold energy while providing the required cooling load. Firstly, the results showed that configuring the solar collectors in parallel arrangement rather than series showed an improvement in solar fraction of up to 5.3%, with an energy savings of 18.4%. Also, a new equivalent volume of PCM to water was found, 62.5%, for this case, contradicting previous research stating equivalent PCM volume can be as low as 10%. It was also found, for this climate, that at least 5 m2 of solar collectors are required per kilowatts of cooling for a system with hot water storage. For hot PCM storage, at least 7 m2 of solar collectors per kilowatts of cooling is required for the PCM to be effective. When modeled with a constant cooling load, the maximum solar fraction achieved with hot water storage was 82.1% and 86.7% with hot PCM storage. Hot and cold test models achieved maximum solar fractions of 85.7% with water and 93.3% with PCM. The hot water model was then simulated with a real, variable building load and achieved a solar fraction of 99.7%.